Okay, so I don't think you should be writing this down. Remember I told you yesterday, maybe one of the two classes, that I'll start off with same thing that we had yesterday. We'll start off with today. The formal definition of what limit is in words. In simplistic form, if the limit of f of x as x approaches a exists, it's only if you approach a from the left is equal to approaching a from the right. This little statement that I have written over there. That is the key, the crux, the main idea of what the limit is. And of course, sometimes you can evaluate these limits in different ways. All right, you can evaluate numerically. That's with a table of values. And that's what I expected you to do on your homework, which I'll collect at the end. And maybe there should be time because the beginning second hour we went over one of them, what I expected you to do on the last 6 questions on your worksheet. And then what we could do is kind of incorporate that into what we're doing today, what you could have done on some of those. But what you're supposed to do is plug in all 6 on your graphing calculator and evaluate the table. That's what I wanted you to do. There it is. Nice. Okay, or graphically, which is the same as evaluating a table, because we could look at the picture. Or we're going to find out today algebraically. Now again, with derivatives, we already did derivatives as a limit, and we actually plugged in numbers after we did something algebraic. So we actually did do this already. Evaluate limits algebraically by working with something. And then, of course, that's where some of my sadness came in. When I looked at some of our worksheets that I did stamp and give back to you, some worse than others, the algebra was horrific. All right? And I do worry about that in an honors class. Some. Again, put your earmuffs on if you're not part of that problem. But you will be marked wrong so quick. Anyone? Your head is spin if that work is not nice and succinct and understandable, and using that limit formula on a derivative, and then seeing all that algebra that gets you to the final result, and then go from there. That's what I'm saying. Let's just put all the classes together. Second and fourth, I would say 30% of us have a problem. All right, and it's algebra. It's algebra 1, algebra 2 skills, and then going from there. All right, so here's this silly first one. Don't take this down. This is what we did yesterday by analyzing a table. Sure, this is a graph of a line. There's no interruptions in that line. So what's the limit of this line as x approaches 2? Well, the answer is 3. And what could I have done to get that, actually? Just what? Plug it in. Because, of course, if the coordinate exists, then when we approach from the left 2 and from the right 2, the y values approach 3 because 2, 3 is actually a coordinate that exists on this graph. That's where the algebraic is going to come in. Sometimes you can just plug it in and be done with it because the idea of approaching is taken care of. All right, next one's real stupid because what kind of line is y equals 4, everybody? Straight. Horizontal. Is that what you're doing? Horizontal. Okay, we got it. Horizontal. All right, so again, same idea as the first example. What's the limit as x approaches 2? Well, it's going to be 4 because any number, 4 exists for that line. All right, now, here's the next one. You can actually treat it as your first example of the day, putting all the ideas together, I guess. What's the limit of this? I don't feel like reading it, as x approaches -1 because you can see it. Can I just plug in -1, yes or no? No, so algebraically it doesn't work. Well, initially, my bad dogs. So what we do with the regular students, which we did this already. I had another set of notes, Cooper's notes, admittedly, where we analyze tables and we analyze what happened. You can't plug in -1, it's undefined, but as you approach -1, you could do this with a regular calculator as well. All right, so if I stole your graphing calculator, well, then you're just going to have to fill out the chart manually and deal with it. As I get closer to -1 from the left and from -1 from the right, it looks like those values are getting close to 3. So you could have answered 3 by the charts. Or you could look at the graph, which I'll talk about the graph after we do this algebraically. You might want to write this down because some of us don't know how to factor. Oh, shot fired. Okay? X cubed plus 1 is a sum of cubes. Fumble. Well, I was late. Fumble. Sum of cubes. Okay, so SOAP Tells me what the signs are. So how you can do it algebraically, if it's possible, is you factor the numerator. There it is. X plus 1 times the quantity x squared minus x plus 1. That's what SOAP comes in. Same, opposite, always positive. Then this cancels, and then I'm allowed to plug in negative 1 into this. What do you think you get when you plug in negative 1 into this? 3. So what is this a picture of if I had to analyze this graphically? It's a picture of a parabola with a hole. There is no vertical asymptote at x equals negative 1. No, 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 no. It's a parabola. I don't know where the hole is located. I don't feel like figuring that out right now. Okay, just as the idea. I know it's located, I mean, as far as what part of the curve. I'm just going to put a hole here, and I'm just going to do this, because that's not really the point. Okay, so that hole is, though, located at negative 1, 3 on the graph. So that hole is negative 1, 3. That's what this all means. So what does y approach as x approaches negative 1? And the answer is 3. That's why this works graphically as well. That's how you'd analyze it as a picture. Okay, then the same thing with this one. What's this a picture of, by the way? As we approach negative 3 from the left and negative 3 from the right. What's this a picture of? Something with what's in it? Asymptotes. X equals negative 3, just to speed this up. Y equals 0. Right. Okay, then I think if I plug in negative 2, yeah, I get a positive. So this is where the curve is up here. Oh, stop. Hammer time. Oh, never mind. I'm thinking of another example. No stopping. Okay, when I approach negative 3 from, I mean, look at this. Look at that number when we actually physically plugged it in. That's a big negative, isn't it? What happens when I put in negative 3.000000001? What kind of number do you get? Really big. What though? Negative is actually the wrong thing to say because it's really small. Blah, blah, blah. It's a mathematician. All right, and then negative 2.99999999999, really big positive. So this is an idea where approaching from the right is not the same as approaching from the left. Does not exist. So I'm going to fast track these because these are silliness and we've already done it. What's the answer to number 1 then? Here's 3 for x. Approach from the left, approach from the right. What's the answer? 3. Oh no, a hole! 2. When I approach 2 from the left, I approach this y coordinate. When I approach 2 from the right, I get this coordinate. 4. It exists. Even though f of 2 does not exist, apparently, for this picture. It gives me maybe a hole, like there's a factor that cancels. So that's not what a limit is. It's about what it approaches, not what it actually is. What's the answer to number 3? Fast. DNE. From the left is not the same as from the right. When I approach this from the left and the right, I'm approaching 2 different y values. And I'm not going to write that down. I have enough left-right limits just to kind of put it all together. Going too fast? What's the number 4? 2. Approach 3 from the left, right, blah, 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 blah. Okay. All right, next one. So 5 and 6 are 2 questions from the same graph. What's 5's answer? 2. 0 from the left, right, we're approaching this, 2. So next one. Does not exist. This one blows my mind. Ask the calculus teacher for sure. She told me. The answer is what? It is infinity. Okay. Because it is approaching infinity from the left and infinity from the right. And those answers. I think we got old. Okay, wait till you see this redonkulous picture. Ah! Hey, come up with the equations that make this graph. Piecewise. Oh, I don't know. Just be quiet. I don't know. Yeah, it does look like a tangent, though. Looks like some tangent. I don't know what's going on. And then, why do we have an open hole here and here? I don't know. All right? Just forget about it. Okay, but look at the picture, and it does its job. As x approaches negative 6, what's the limit of f of x? as x approaches negative 6 from the left and from the right. What do we get? Negative 4. Hey, by the way, what is f of negative 6? Look at the picture. No, it's 1. You may not be able to see the dot. See that dot right there? That's a piecewise. What are you laughing at? That's one of those things from second hour. Okay? 6 left and right, negative, sorry. It approaches negative 4. You know, kind of show that as I like showing it on the curve. But f of 6 is negative 6 is defined by 1 by that dot. That's just a piecewise function, no big deal. Ain't no thing anyway. Negative 1. It's like a sauna in here, isn't it? Negative 2. We okay? Got it? Any questions? Stop me. 2. 2. DNE. I bet you said infinity. I was like, what? 7. 1, 2, 3, 4, 5, 6, 7. Here's 7 on the x-axis. What's the answer? Ooh, no, because the graph actually exists here for 7. That just kind of, you know, this, whoever drew this, it kind of skipped. It's right here. So what is the answer? DNE, because there's difference when I approach from the left compared to the right. Not that these aren't. Do I really have to do this one? There's a question. Oh. Let's skip that one. What was that? Okay, the blue axis, the blue x and y axis. So the first one, I'm going to skip around. These are all cattywampus. Okay, as 2, 1, 2 approaches from the left. What does y approach? 4. It's 4 up. Now, and I should have assigned left-right limits too, because the book does have those in the book assignment. It's a book assignment today. I'm going to go 2 plus, skip to this one. What's the answer to that? 4. So what's the limit as x approaches 2, period? 4. And that's a continuous graph, although it is a piecewise where they just the pieces happen to connect. So, yeah. 5 from the right, 1, 2, 3, 4, 5. 5 from the right, 1, 5 from the left. So the limit as x approaches 5, 1. 0 from the left. These are all stupid. 0 from the left, 0. 0 from the right, 0. What would have been better is negative 2 from the left. What's the answer? Negative 2 from the left. Oh, it's right here. I'm so stupid. Mark it. Oh, I knew it. Right. Finally admits it. All right, ugly and stupid, like in 4th grade. All right, negative 2 from the left, what is that? Negative 1, what's happening? Negative 2 from the right, 2. So what's the limit as x approaches negative 2? DNE, there it is, because 15 does not equal 17. Then, of course, where's number 16? All right, get it, because 16 skipped. Never mind. What's the limit as x approaches infinity according to this graph? Looks like it, doesn't it? So we'll count it that there's some sort of weird asymptote going on there. X approaches negative infinity. 1, 2, 3. You're right. So then what do you think the limit of fx is as x approaches negative 10, which is way out here somewhere? It's still 4. Okay, so you can count that that's continuous because the arrow says it is. All right, now some simple algebra stuff. Hopefully this puts it all together. So how can we do limits? Table, analyze the graph, or sometimes algebraically we'll do the trick. All right, and then that's where we might need some help with what I do today, our algebra skills of factoring and dealing with fractions within fractions, square roots. Sometimes you want to rationalize the, anyone? Numerator, okay, and then that's the kind of stuff that I did not see on some of those derivative worksheets. Disaster. That is spelled with an extra R. It's worse than a disaster. So, is there a problem with plugging in 2 There is a problem with this. That should say Y. I just noticed that. Second hour found it. Look at that. He screwed up again. All right. What's the answer? What's the answer? 10. You are allowed to just plug in 2 because there is no issue. And then you'll be assured. What is this a picture of? Parabola. And then you'll be, well, don't get too literal. I got you. But let's just do that. Don't worry about it. They're just playing with the letters. Doesn't always have to be X. It could be limit as Z approaches 0, Z squared plus, whatever. Gotcha. But at 10, at 2 comma 10, let's just pretend. I have no idea where it's at. That point exists. So, oh, I thought you were sleeping. You're just making notes on this. Okay. Anyway, let's move on. Yeah. Pay attention. Ah! Okay, next. So, you just plug in because there is no problem. Then you're assured that at this graph, the graph will be continuous. Q root of 27 is 3. By the way, does this graph go from infinity to negative infinity? Is that the domain? And actually the range? What's the cube root of a negative? A negative. So is the domain and range infinity to negative infinity? Reverse that. I went out of order. Another mistake. Okay, now we get into it. And I think we talked about this yesterday a little bit already. And actually, I already did with our example with the chart. Can I plug in 6 right now? Yes or no? No. I am taping, right? Okay, good. 16 minutes. Oh. Okay. All right. No, you can't. So now what do we do? Table. By the way, plugging this in your graphing calculator, then getting the zoom maybe right away. You don't even have to look at the picture. Getting your table set up the right way, and then going to the table. Is that short or long? Long. And that's why I yelled at second hour, and I yell at you. You should not have been given extra time on that quiz that I gave you Wednesday. Not. Here comes the diatribe. You know what a diatribe is? A negative rant. Are you ready? Okay. You ran out of time because I had some goofballs, and I should have made it more of an honors test. Like, let's give an example. The sigma section. By the way, that sigma section was from your chapter 2 test or your chapter test from last year. I pulled those same questions. I changed some numbers. This is one of the tests. Do you know how to work with a sigma? Unfortunately, I only had sigma like for 14, 15, 16 terms. Remember I made the joke about the kid that had like 80 terms and he wrote all 80 of them out and then got an answer? Oh, he was right, but he got one question done. Because how long does that take? Forever. You know how simple those questions are if you actually know the formula? All right, and that was a problem. All right, a big problem, some more than others. Some bums, that's what I said, it's on YouTube, found the sigma button on their graphing calculator and thought I could use that every single time and just put answers on my whole test. Guess what they got? An F. Okay, because you know why? I could teach my 9-year-old and 11-year-old those buttons and then show them the questions on the test and say, okay, just emulate those buttons on this graphing calculator. It would take me less than an hour to teach them to do that. The point is, do they have any idea what they're finding or what they're doing? No. And that's what you're demonstrating as well. So why I'm going through this is when you go to a chart, instead of doing this algebraically, you've just cost yourself major amounts of time on a quiz. You're your own worst enemy. Okay, so here we go. And it needs to be said because some of you don't get it. And there are times where I take my moments to be a jerk, and this is one of them. Okay? And shaking her head. I love that shaking head. Yes, you are. All right, that's fine. All right, so what's 36 minus x squared? That was fun, wasn't it? Okay, what happens? They cancel. What does that mean there's in this picture? A hole, and I'll actually draw this for your entertainment. Okay, but this is 1 over. Okay, he goes, yes, I can't wait. What's 1 plus 6 over 6? Okay, so now this is what this means. Let's go to this. The graph of this is this graph, y equals 1 over 6 plus x. It's the exact same graph as this, except this one has a, say it again, hole. Where's the hole located? At 6, 112. That's why when we evaluate this limit, the y values that approach when we go to the left 6, slow down. When I jump just to the left of 6 and just to the right of 6, the y value we're approaching is 112. So I'm going to graph it for your fun. Where's the vertical asymptote? No time. At negative 6. Where's the horizontal asymptote? 0. I'll mark it on so quick your head will be, it's y equals. Right? And then here's 6, 1/12. And then this graph does this. Oh, I gotta watch myself. My pen's in the way. There we go, moved. Hole. Then it does that. Then the other graph is right here. So what happens when you approach 6 from the left and 6 from the right? What y value we're approaching? 1/12. That's what this all means about limits and why it works this way. I don't know what else to tell you. Okay? So I thought I'd just add that in for fun. Oh, no! Can I plug in 5? Okay, so what's 3/5 minus 3/5? 0, so I can't do it. Okay, now this is the algebra that is actually where some of us just, the derivatives, this was bad. What do I multiply top and bottom by? Very similar algebra. 5x. Now I'll take a break after this one. Let me take a break now. I'm breathing heavy. Just do that. All right, so here we go. We're back. Limit as x approaches 5. Do not distribute the numerator. Remember what you're trying to do, especially when we're talking about those derivative questions, slope of tangent lines and all that. You want to see something cancel. All right. Now, when I distribute this, what happens? Who cancels? X, and you're left with 5 times 3, which is what? 15. I can't help you on that. That's algebra 2. We started the year off with this kind of stuff, I believe. And then what cancels here when I throw the 5 in there? 5, and what am I left with? Minus 3x. Still not there. What should I take out? A 3? Just show everyone what we should actually take out. So we really see what's happening. Not 3, but negative 3. Because what does that turn this bottom factor to become? X minus 5. And then we're not going to think about this graphically. I should, actually. Because you know what this is a picture of then? What's this a picture of? What's this a graph of? It's a line. What's the slope of that line? Negative 5/3. But there's a what? Hole. Where's the hole located? 5, negative 25/3. The answer to the limit is negative 25/3, though. So talking about holes. Love it. We're putting it all together. But wait, there's more. All right. Okay. Not to go too fast. That's why I'm stopping for a second. What's the top factor to become everybody? By the way, can I plug in 2? No. So what's the top factor if it does? What's this really a picture of? With a hole located? 2, and the answer to the limit is the y value that it approaches, negative 1. Oh, this drives me crazy. Can I plug in 5? No. What happens? Soap. Same, opposite, always positive. It's the old a cubed minus b cubed thing. The first thing is a binomial. Then it's the first term squared. Opposite. The two terms multiplied together. Always positive. The second term squared. That's the pattern. And of course, if it was a sum of cubes, what does that become? Plus, what does that become? Same, opposite, always positive. So that's what the change be. Okay, so I did my teaching. again, of factoring. Shipow, what's this a picture of? Parabola. It has a what, though? Hole at what? 5, comma 75. When I plug in 5, I get 75 for a y value. That's what it's saying. What y value does it approach as we approach 5 from the left and the right? And the whole idea would take care of that. Holy crow! Now, these are the ones, honestly, that I stole from Cooper's notes. And actually, they are ones that you'll see in your homework. So instead of me making up my own, I just stole hers. I'll give her credit. Deserved. She's directing where we go on this, and it's awesome. Ooh, this is strange. I think what you could do... What did we do when we had derivatives of a root, and then we had to do the root and all that? You would rationalize the numerator. I think that might work with this one. But I have another unique way of looking at this. Did you know that this is a difference of 2 squares? What? Are you serious? What times what equals x? Square root of x. What times what equals 4? 2. And watch what it does when I do that. Limit. As x approaches 4, make enough space, yeah. Root x minus 2 over root x minus 2 times a root x plus 2. Good FOILers are root x times root x, x. 2 root x and negative 2 root x. What happens? Negative 2 times 2? Negative 4. Shapow. What's this a picture? Oh, I actually don't know. 1 over a root. I'd have to see that as a picture. But this picture certainly has a what? Hole. A hole located at what? Oh. What's the square root of 4? 2. 2 plus 2. 1 over 4. I better do that one. This ends up being 1 over a root x plus 2. Why don't I write lim as x approaches 4? Because I plugged it in. That's when the lim drops. You lazy bums. I did it again. Is that twice? 5 times? No, I think it was only twice. Let's check the tape. When you drop the lim as h approaches 0, when is that not in front of your derivative formula? When you've actually what? Plugged it in. I'm going to take a point off for every time the lim as h approaches 0 is not in front of each set of work. Because that's how insane I am. Now, you think something like that can happen with this one? What I just did over here? Yeah. I mean, this is root y minus root 3. Root, what? I'm done. Okay, now, you know what you should try? I don't know why I put those, but what should I try? Multiply both top and bottom by this just to see what happens. And if this doesn't do anything, what could you do as a last resort? Analyze the table. Okay? Now, you're not going to do anything with the numerator. The whole point of doing this is to see if something cancels. So I want the numerator. We'll get rid of that extra set of parentheses that were unnecessary. Just to see if something happens in the denominator that cancels with the numerator. And then, because we can't plug in 3, what's 7 minus 3, everybody? I should have said that first. What's 7 minus 3? What's the square root of 4? 2 minus 2 is 0 in the denominator. This is why I have to proceed on algebraically. Now, down at the bottom, this is what's driving me nuts about rationalizing the numerator. People that didn't do this correctly on the derivative worksheet that I collected and almost threw up on. What is 2 times 2? 4. What happens to the middle term? I don't even want to look at them. This is the point of a conjugate. If you don't know that at this point, it is a problem. And then freedom. I wish I had freedom from this class. All right? 7 minus... I wasn't saying that. I was being a student. Freedom. And then what happens? What does the bottom become? Distribute the minus sign. And what does the bottom become? Y minus 3. Ultimately, if you rework things. And then what you can do, what time is it? 50? Oh, okay, yeah, so I'm flying faster. But depends a second hour. We actually did a question from the worksheet, so that's why we fell behind. a little bit and went to the bell. Shapow. Okay, so now what should I see next is this. 2 plus 7 minus 3. What is 7 minus 3? What's the square root of 4? What's 2 plus 2? It is 4. I had to think about that for a second. No, it's not plus minus 2 and then it. No, that's when you solve. You know, what's the answer for this? What's the answer for this? Plus minus 2. What's the answer for this? 2. What's the answer for this? Negative 2. What's the answer for this? 2i. What's the answer for this? What's the answer for this? Plus minus 2i. Because both of those work for the equation. That's the only time you really, not the only, I don't want to get stuck with an only, but when you're solving an equation, that's when you've got to worry about those plus minuses. That's the coming after you and your family wording. Remember? Sorry, thrilling YouTube. Ooh, watch me erase. All right. What? Okay, look at these rules, because we're going to use them. You're not taking all these down. Okay, this is what it says. Oh, Chromebook, and I love it. It's my favorite. Okay, now, thumb rule for derivatives. If you could see that you're taking derivatives, I said limits, I meant limits. Oh, a mistake. All right, limits. If you can see within this, you have a limit of a sum of two functions. If you could see that within there, then what you could do is take the limit of the first part and then add that to the limit of the second part. You could break them up. Now, I'm not going to read through all of these rules, but we're going to use quite a few of these, and I may come back to them. Like, let's look at this one. Limit of a function divided by a function. Well, what you could do is take the limit of the numerator, the limit of the denominator separately, and then divide those two limits. So these are giving you options of the things that you can do. Look at this one. It's real semantic, and some of you make this mistake. Like, if negative 3 is the R value in a geometric, thank you, geometric, you didn't say that, geometric scenario. So say it's a sub 1 times negative 3 raised to the n minus 1 power. Is that correct, how you wrote that? No, it is not. You're actually saying 3 is the R value, and there's just a negative floating there. So why I discovered that, why my brain just went there, there was mistakes semantically, or syntaxically is what I meant to say. So look at this one. You may not see a difference in there, but there's a huge difference. That's why I went through that. The limit of x as x plus z of f of x raised to the nth power, what you could do is find the limit of f of x and then raise that limit to that power. That's a major difference. And that's why I went through all that, as someone's rubbing their eyes out like they want to forget that just happened. So it's an important thing. All right? So, hey, this is your favorite. Okay, we're going to analyze this before we use it. Now, given the limit as x approaches 0, I keep saying it wrong. You say the limit of sine of x over x as x approaches 0 equals 1. Find. Well, before I wanted to do that, I wanted to prove, or at least show you, two different ways that this is true. First way, I think I already have it ready, because that's what I typed on my calculator the other hour. Oh, and I put a couple other things that I'm just going to cheat. First thing I did is I put that in my y equals screen. And then I'm going to analyze the what? Table. But what I have to do is make sure, mode, I'm in radians, if you wanted to play at home with this, and then zoom trig. All right, because I just want it to work out that it looks like, the picture that I need. Well, I can do this graphically. Here's 0, and then what does it look like the y values approach? 1. And actually, I have to know that I cannot plug in 0 for x. So what's going to happen at 0 on the table? 0 is going to be what? Undefined. And how does that look like on a graphing calculator? Well, first thing I want to do is set up my table to be at 0 for the starting point on the table. I want to go by small values incrementally, 0.01 above and below. This is how you should have done the last part of your worksheet. Oh, it actually says error. I thought it used to say just blank. I think an old-fashioned calculator would just have a blank there. I'm not sure if that's true or not. But look at those y values. What do they look like they're approaching? Both sides are approaching 1. Or, what I said is I did this if I didn't have a graphing calculator. I just did the sine of negative 0.01 divided by negative 0.01. Then I did the sine of 0.01 divided by 0.01. You can do a couple more tests and get closer and closer and closer. The closer you get, it approaches 1. So, with that being said, we're going to use it algebraically for these questions. Now I know I need more space because the other hour I kind of ran into space issues. I'm going to slide this up. And then all this becomes now is an algebraic scenario. Zoom in, and then I'll show you the first couple. And again, this is right off of Cooper's Notes again, give credit where credit's due. And really what it comes down to is just dealing with fractions appropriately. What am I? Fraction jerk. And then there's other things in the hallway. Save that for the hallway. Save it. Not interested. Oh, it hurts a little, but that's fine. We can move on. Okay, so the first thing is, fractionally, the common denominator rule in reverse should be used. Right? Okay, now I'm going to break this down. Limit as x approaches 0 of x over x, true, plus sine of x over x. And then I'm going to go back. This is going to be dizzying. You ready? I'm going to go back to the sum rule. Very first one in the chart. The limit of a sum, I can find each individual limit and then add them. So that's what I'm going to do now with this one. By the way, what's x over x? Plus the limit as x approaches 0. I keep saying that the wrong way. Sine of x over x. The limit of sine of x over x as x approaches 0. So what's each one of these? What's this answer? It is 1. Remember what that horizontal line thing? This is a horizontal line. You know, I plug in 0, I get 1. So therefore 1 is a continuous point. So the answer to that limit is 1. What's this one? That's the given, everybody. So the answer is 2. That overall limit equals 2 when you're done. This is the work that you would show to prove you know what you're doing. Not, 2, Mr. Samuelis. Doesn't work. Some people are still beating your heads up against the wall, being in this class. Actually, I'm not even as bad as some other teachers. Wait till next year. So I'm trying to train you for. Next year is going to be trouble if you still do what you do. What's 1 minus cosine squared? Whoops. Okay, so this is the limit as x approaches 0 of, I guess I could get away with saying that, sine squared of x over x squared. Oh, let's save some time. Isn't that this? Right? Let's do that. And then say that we could do this. We could find the limit as x approaches 0. And then square that. And I'm not scrolling back up there because I already showed you that and made a point. And someone tried to rub their eyeballs right out of their sockets. What's the answer? 1 squared. But wait, anyone? There's more. I think this one is the same. Cube root over cube root. That's the same as taking, okay, fine, it's a power rule. What's a cube root the same thing as? Raise it to the 1/3. What's the answer? Still 1. Because 1 to the cube root power, 1 to the 1/3 power, said that weird, is 1. Now you really need me. Now this is what I told the other hour. Watch these because I ran out of time, these last two. Because I love them because all they are fractional conundrums. And they are tough. Look at that. That's mine. I made this one. Is there a rule that says I could do this? Sine of x over 4x squared minus sine of x over x? Heck no, I almost swore. Alright? So this is what you got to do. Take out in the bottom. I don't have time for this. Take out an x. Now watch how I restructure this. 4x minus 1, because I'm going to do a bunch of things at once because of time. You have this, right? Right? Times this. I just want to throw a 1 in there so you see something, right? And then what I'm going to do is use the product rule up there. The limit of, if you can identify the limit of something times something else, what you can do is the limit of the first, and then multiply it by the limit of the second function. What's this equal to? 1. What's this equal to? Plug in 0. 4 times 0 is 0. 0 minus 1 is negative 1. Negative 1. So the overall limit's negative 1 of the original question. Isn't that fun? It's just algebra. And it's fractions. Who's a jerk? You are, Mr. S. And then this is when I ran out of time. Whether you walk out of here or not, just like a second hour when I was showing that Hubble telescope, I got trampled. I almost got killed. I had to go to the nurse office because 10 students walked over me to get out of here before the Hubble telescope video was over. And I'm finally healed today from that. Okay, now this one's back to our old school, but there is something hiding in here that's a little tricky. Limit as x approaches 0. We know we can break this up into 2 separate fractions. By the way, what does this become? Plus the limit as x approaches 0 of the other fraction. Whoops, that's not that. Which is 2 sine x over 4x, which becomes sine x over 2x. And then I'm going to do the same thing I did with the previous example. Times 1, right? Now I have a limit of a product. I'm going to write this all as limits before I actually evaluate. Limit as x approaches 0 of 1/4 plus the limit as x approaches 0 of 1/2 times the limit, I should put this in little brackets, the limit as x approaches 0 of finally the sine x over x by itself. What's this one equal to? What's this one equal to? 1/4. What's this equal to? 1/2. What's this one equal to? 1. And then all you have to do is add 1/4 plus 1/2. You'll learn how to do that in calculus. It's another fraction shot. Is it 3/4 last time I checked? All right.